to make sure that this is recording. Okay, so let's remember where we kind of finished last time. What are we looking at here? What is the large graph on the right-hand side? Anyone remembers? It's written dynamic amplification factor, but this is on a spectrum. So it's kind of a normalized amplitude spectrum. You can think about it that way. It's very, very important. That's why let's look at it a little bit more today. Again, my numbers don't show up here, but they're kind of important. A few numbers are important here. What we are looking at is the amplification factor, which is nothing else but the response of the system divided by the static response, the absolute value. And this red curve corresponds to a damping ratio of 1. And as we go towards the other curves, the damping ratio is decreasing. Now, the x-axis is a normalized frequency. If you remember last time, that's the excitation frequency, the input to the system, normalized by the natural frequency of the system. And when I say system, I'm basically talking about this very simple single degree of freedom system that we have been talking about. So with a viscous damper dashpot and a linear spring. Now, we made a couple of observations last time, and that was that this maximum, especially for a smaller damping ratios, happens at what frequency? You can see it. I'm asking about the maximum, the observations, what this plot is telling us, what's important here. So the maximum of dynamic amplification or magnification factor happens at what frequency?
Just below the natural.
What does it mean? When omega is just below 1, what does it mean exactly? That means that the frequency input to the system is just below the natural frequency of the system. Yes? This is a forced vibration response. Just below the resonance. So this is like omega is just below 1. So what you're inputting to the system is very close to 1, almost equal to 1, but not quite. That's what it means. So that means that if you are running a system with a force which is around its natural frequency, you are going to get this large magnification. And this is the concept of resonance. That's what it is. Actually, you can calculate where you see exactly the maximum of m, and that happens exactly at omega square root of 1 minus 2d squared. So now you see that y, if d is very, very small, as you go towards the black curve, this occurs at a, let's call this maximum, it becomes almost 1. We also looked at the phase. Let me not take this so fast. We also looked at the phase here. And you see the phase corresponding to this phase corresponds to, now it is purple here, but this is also damping ratio of 1, which we called last time, what did we call damping ratio of 1? Anyone remembers? Critically damped. It looks like this, but you see that as you decrease the damping ratio, what do we see around omega equal to 1? What is happening? But you see that the curves have an inflection point there. They change curvature. So at the resonance, if you look at the phase of the Fourier transform, so this is called a phase spectrum. That is amplitude spectrum, this is phase spectrum. You see a change in curvature. So there was one more thing I told you, and we are going to go back to it today because it's very important about accelerometers. So I brought an accelerometer to show you if you have never seen one. If you have seen one, you'll see another one, I guess. But it's very important to look at some of these curves. For example, look at this one. So this curve, it corresponds to a damping ratio which is less than 1, but it's pretty much damped still. It's not much less than 1. And you see what is happening. It's around in this frequency range. So I call this a frequency range. It's just a... You see that the dynamic magnification factor is pretty much 1. Now, if you look at a similar curve, here it's like the blue curve here, for example. The phase is changing over this frequency. It's not constant as much. Keep this in mind, we come back to this in a second. So this is what we talked about last time. The last thing, no, maybe first, I forgot that. I wanted to also kind of put together all the ideas about damping. Last time I told you that what is interesting from the damped forced vibration is that typically, I don't know why I have this here. When we have, let's say you have a system, you have a piece of material, something, and you want to know more about it. And you apply a force, let's say you just tap it with a hammer, and then you have an accelerometer, which very soon you will see what it is. And you record the vibration. And since it has damping, almost any physical system has, the response will look something like that. This is what we talked about last time. And a lot of times, this is the response you have selected, and you want to know what are the material parameters. And we talked about damping, so you want to know what is the damping of your system. So last time I introduced this concept of logarithmic decrement. So what was it? I thought, okay, you can take time n and time m such that m is n plus m minus n times the damped period of the system. That means that I'm looking at, let's say, maxima. I'm just going... Last time I just said, okay, let's pick the next one, but we could do it if you pick the next one or any other one. Anyway, if we have that, I showed you that the logarithmic decrement, you can calculate it by basically taking the amplitude that you have at here and here, so you just divide it, and this is logarithmic. That's why it is called logarithmic decrement. And I showed you why we need to use logarithmic, because this, you saw that this follows an exponential function. For this simple system, it looks something like that. That's why it all makes sense to have this logarithmically. Anyway, so I also showed you that you can relate this delta to damping ratio. These are related to each other. And if the damping is very much smaller than 1, which is typically the case, then you can approximate it as 2 pi d. Now, this is how you would calculate damping in time domain. So let's say if you had a time signal and you had this nice signal, you could basically fit an exponential to it, and you can actually very easily get delta and d. But we typically don't do this in the time domain, and the reason is this is very easy in the time domain if you only have one frequency. Most likely you don't have this situation, and damping is highly frequency dependent. So typically the higher the frequency is, the higher is the damping. Just high frequency vibration or waves, they dissipate much faster. So because of that, a lot of times we actually do damping calculations in the frequency domain. And the frequency domain, let's say it looks something like that. At one frequency, you have a peak, and here is the maximum amplitude at that peak. Remember, this is only good for one frequency. And then you look at half power amplitude. So half of the power means that you divide the amplitude by the square root of 2. Since we have discussed this before, I make it a little bit faster. So if you kind of see where you hit, I think you did this in your homework, so it should be now very, very easy for you to see. And this is what we call half power bandwidths. Try to get used to this terminology, bandwidths. That's what we use for frequency range. I don't know why, but that's something everyone uses, frequency band. You don't normally say frequency range, you say frequency bandwidth. Now, there is a very useful relationship between these parameters in frequency domain and damping ratio. So it turns out that the damping ratio is, you can show that this is the case. And if we write it in English, this is half power bandwidth, and this is 2 times center frequency, which is FC. So the damping ratio, let's say if we show that by delta F, over 2 times Fc. So look, you can, in time domain or frequency domain, you can get the damping ratio. And if you don't make any mistake, you should get the same number. And in the next homework that I don't want to talk about much about today, because you just finished this homework, so don't think about it. That's one thing you will do, and you see for yourself that in time domain or frequency domain, you are going to get the same damping ratio. Now, what we like to use a lot of times is this quality factor or Q factor. Quality, so, and that's very related to all of this. That's the center frequency over half power bandwidth. Just the definition. So it's kind of 1 over 2D. So what we need to kind of be careful about is that higher damping means lower quality. To remember that, you can think that, you know, whoever has defined it didn't like damping, didn't like highly damping materials, so that is considered low quality, if that makes any sense to you. So now, if I ask you this question, that let's say if you have aluminum or steel, and if you have rock, and if you have concrete, so which one do you think has the highest Q factor? Which one? Aluminum has the highest Q factor. So if I rank them in terms of Q factor, the Q of aluminum is larger than, I mean, just typically, I don't want to go to the details of one rock versus the other. I know some of you know a lot more about that, and also concrete depends on a lot of things. So just typically, the Q factor of rock and concrete, typically, based on my experience, rock is a much easier material to work with than concrete. That is because if you look at the damping, it's kind of the opposite order. What does this mean? I mean, if you look at, let's say, if you look at a resonance signal, for the lack of better term right now, for, let's say, aluminum, that would mean that it's going to ring. We call this ring for a long time. This is the same for steel. They have low damping. That means that once you excite them, this wave is going back and forth everywhere, and you are going to have this kind of ringing. We call this ringing sometimes. Now, if you do, so this is, let's say, aluminum. It's not the nicest waveforms I could have made here, but let's say if we take a piece of rock and we apply the same kind of loading, everything, I would expect that, you know, it's after a while it is pretty damp. And then concrete is a very hard material to work with, and that would probably be here. It's much higher damping than rocks. So that's what Q factor means, and it's a very useful thing, and that's just kind of a review of the things you already know. Now, these are useful things. The last thing that I like to kind of for the sake of completeness, to finish off the vibration with is when we have arbitrary loading. Why this is important? Because there are a number of concepts here that are very helpful later on to understand some of the other concepts. So why this is a new topic? Because so far, if you remember, when we looked at force vibration, we just looked at harmonic loading. We didn't do anything else. I did a magic, took Fourier transform from both sides and got a really nice results, and that's what we did. So the kind of concept that I want you guys to see is that this is the equation of motion. You should be able to write this down like very easily. And the force right now is arbitrary. So something very easy conceptually is that, okay, if we know the answer to harmonic loading, didn't we say that every function can be written in Fourier series? So that makes everything very simple. So meaning that we can just write this now arbitrary function. We say, okay, we write this in the form of Fourier series. No matter how arbitrary this is, we can see that it can be written in this form. A summation of harmonics. Everyone agrees that we can do this with any arbitrary time function. We can do that. So that makes everything very easy, because that would mean that the solution to this equation is just a summation of all these solutions. Conceptually, this is important. And we are not going to solve it, but it's kind of important to realize that Fourier transform is very useful. So the solution to one of these, last time, we saw that it would look something like that, Pn, and that's the amplitude in the frequency domain, the kind of uppercase, and then it would be I omega n bar, that's for excitation frequency. Basically, this is what we had last time for one single harmonic. So for each component, for the nth component, we can write that solution because it's a harmonic loading. So it looked something like that, not to make any mistakes here. And I don't write this any more than that, that the final answer would be nothing else but the summation of all these partial solutions. Does everyone agree with this? Is this clear to everyone why we can take the arbitrary loading, write it as a series of bunch of harmonics, and since we know how to get the answer to one harmonic, we just sum it up because it's a linear system. Of course, things will be different if it's not linear. We can't do that. Now, this is kind of important concept. There is another way of looking at this problem, which is important because it introduces the concept of impulse response. So I call this impulse response approach. And I just show you in a very simple way how it works. I don't intend to go through the whole details of that. First of all, let me see if this notion of impulse response mean anything to any of you. When you hear impulse response, Is this something which means anything to you? Have you ever encountered this before? What does it mean? It's the response of a system to a Dirac delta function. That's a good answer. And it's a very useful thing, because when you know the response of a system to just a spike, then the response of any system will be an integral of that system. That's why impulse response is very important. So let's just very quickly see how this applies here. Here is the arbitrary loading versus time. So arbitrary can be anything. It doesn't need to be a harmonic or anything like that. So the way this is set up is that you just take one really tiny part of this loading function at time tau. So the amplitude would be p tau. So now we know what would be the response of this function to p tau d tau. That's just an impulse, right, to the system. So this will be the input, and we assume no damping, undamped. I just want to make this simple, undamped response. We know that the response to an undamped system is just A, or let's write it better, Z0 cosine omega t plus Z0 dot over omega sine omega t. This we know that. So the response here will be then Z. I call this, I want to use the same notation as I have in my notes. I call this dz of t, because it's just a response to one tiny part of the load, and it would be z dot, which is the impulse over m. This is just like the example I solved for you when we had a frame and it was just being excited. So this is z dot over m sine omega, but this is valid for the t's which are larger than tau. Meaning that if you just consider this simple impulse, the response to just this, hatched area would look something like that. And this is t minus tau, because before that this doesn't exist. Does it make sense? And it's a sinusoidal with this amplitude. Okay, this is pretty much, we are almost done, because we have this response to this. For the whole response, we calculate the integral. So if we have the response to one single impulse, now the response to the whole force would be the integral of this signal. And this is what it is important to look at this integral, and you will see that. So if we write this as p tau, and then, well, we have now two d taus, we don't need both of them. So I just move it there so it looks nice like that. So 1 over m omega sine omega t minus tau d tau. So what is this? What type of integral is that? Let's make it even easier. If I call this h, so let's recap what we did. This is a completely arbitrary loading. We just take one impulse out of it, just over very tiny time theta. The response to that, just like what you saw in the example that we solved before, you can go back and look at it, would be z0 dot over omega sine omega t minus tau, because before tau there is nothing. That happens at tau, and then it happens afterwards. So then I just take the integral. What type of integral is that? It's a convolution. So that's kind of the important part of this whole thing, is that the response is actually a convolution of the forcing function and the impulse response of the system. So if you know the impulse response, you can always calculate the response of your system to any type of loading you want. You just calculate that once, and you can always use it for any type of loading. And another thing here, which I like you to remember, is that in frequency domain, the convolution becomes multiplication. Meaning that in frequency domain, the response is just the frequency representation of the load, the spectrum of the load, and you may think about it that way, times the impulse response in frequency domain. What does it tell you? If you want to know the impulse response of your system, and you have the response, and you know the load, all you have to do is just divide them, and then you have the impulse response. You can go from frequency domain to time domain. This is very important, just this whole concept of what's happening here. More important than how it is being used here. Any questions? Yes.
Can you describe what h of t minus tau is again?
That's, I just replaced 1 over m omega sine omega t minus tau by that. And that's the impulse response of the system. Why I say that? Because if the force is p tau, that's the response. It's an undamped response. If I make this 1, that just looks like sine omega t just over m omega. So it's just kind of a normalized version of that. It will look different if your system has other damping, but for the sake of just that you see the concept, this simple case is enough for you to see what's going on. I don't want to go through all the details of that. The concept of Green's function, for example, is very similar, kind of very related to that. So it's useful to know. Now, there is I put an example, but you can look at it in in the notes. I don't go through it. I jump to the kind of the last part for today, because we need to go to Chas class, and that's the working of an accelerometer. If you never saw an accelerometer before in your life, here is one. It's actually a damaged one. But if it was not damaged, you have to be very careful with accelerometers so you don't drop it. And it's a miniature. It's a very small one. If you open it up, inside there are lots of things, amazingly, but it's very tiny, this one. A lot of times you don't want your accelerometer to be too big to influence the resonance behavior of whatever you are measuring. So that's why we like accelerometers a lot. Now, it's important to understand why it works, and it's very related to what we have learned. It's a nice conclusion, let's say, of a single degree of freedom system. So you may very simply model an accelerometer with a single degree of freedom system. So this is the housing of it. That's how it looks like. And then inside you have a mass, and then you have I put it up here. You have a spring, and you have a damper. And the ground is moving. Let's say this is ground. This ground can be a specimen. Doesn't have to be like ground. And I took positive upward for both. And the mass, the absolute displacement is upward like that. It's more like an application of what we learned, or any, rather than being something new. Very quickly, if you look at the free body diagram, we have force. So I took the movements upward, so from both the spring and the dashboard. And then we also have, this, already, that's the inertia. I don't like to, I like always to differentiate that. So, because the housing is, because you place it on the ground or on a specimen, depending on your application, the housing is moving with the specimen, right? So the spring is between the mass and the housing. So the force would be, I hope you agree that it would be like Z minus ZG. And the same thing happens with C, because they react to the relative displacement, not to the absolute. But this is not the case for the inertial force. And now I just write the equation of motion. And I call this Z sub R, R for relative. Now it turns out that it's easier to write Z in terms of ZR and ZG. So Z minus ZG is ZR. So you can write everything in terms of ZR very easily. That's dot here. C ZR dot K ZR, and then the M ZG dot goes to the other side and becomes negative. Yes, everyone is okay with this? And now, to understand this, let's assume that this ZG is harmonic. Because you saw that if we understand the harmonic response, we can understand the response to any system. Because we have Fourier series. So we assume that it is harmonic with an amplitude ZG and some frequency that it is being entered. So if we do that, this is acceleration, so you get I omega 2 times negative omega squared, right? So it becomes m omega squared ZG E I omega t. Now, this looks exactly like what you have seen before. I hope you see that. This is like now the PT, which is actually a constant. It is the P0 is just this constant here that we have. And that's E I omega bar t. So we can write the amplification factor M. So it is ZR over basically P0 over K. This I don't write down why. This is what we have discussed last time. So P0 is now M omega, and this is omega bar. Even I should be careful about that. This is omega bar, and this is very important here. ZG over K. Okay. And we can write this as omega bar squared over omega n squared, because this is K over M of the accelerometer. ZG. And we know what this relationship is. Now, the question is, for an accelerometer, what do we want? What do we want this to be? I showed you previously in the first slide, I showed you that what we like to have in accelerometers is that this m be equal to 1. Let's see why. So if this m is almost 1, ZR is almost equal to omega bar over omega n squared ZG, right? We can write this differently like that. What is this? This is the acceleration that we measure with the accelerometer. The output. That's what we want to measure, the input. And they're almost equal. That's why we like to have a magnification factor which is around 1, because of that. Because what you want to measure, you want it to be in the same order of what you are actually getting from the ground, right? Now, to do that, you saw here that we need to have, let's say, in this case, the damping ratio is about 0.5. So there is another catch to that. You want to have, at the same time, you don't want this to be very, very small. Because if omega n is very large, then ZR becomes very, very small. That means that your accelerometer won't have good sensitivity. Okay? So from one side, you want to make sure that omega is small. That means that omega n is relatively large, so that m is around 1. Look here. This happens for some omega which is less than, let's say, 1. So you don't want to have omega which is much larger. So because of that, you can't control the excitation. What you can control is the frequency of, the natural frequency of the accelerometer you are designing. So because of that, you want omega n be large. Okay. So that you get m almost equal to 1. From the other side, you don't want it to be too large, because otherwise the R becomes very small. There are more details in the notes. I kind of look at the watch so we don't miss the meeting. But I want you to look at this. What I'm giving to you is the specification of the accelerometer. What you see here is nothing else but a Zoom-in version of the curve that I showed you. So you see that how m is changing for different frequency. On the other side, you see both phase and amplitude over the larger frequency bandwidth. Make sure you understand this, because in your next homework, if you don't want to talk about it, I ask you to design a displacement sensor. So to use your knowledge to design a sensor which can measure displacement. This one is good for acceleration. You see, if m is equal to 1, the acceleration that you are getting out is similar to what you are putting in. How do we get around 1? You want omega to be small. That means you want a stiff accelerometer pretty much to get m equal to 1, but not too stiff, because if it is too stiff, it's going to give you very small, let's say, electric charge, very small output for the same input, and that is not good. That means that it's not sensitive. So you need to find some sort of a compromise between wanting your accelerometer to be stiff and at the same time not too stiff. Now, if you want to design a displacement sensor, it will be a little bit different, but the same concept. You have to play exactly just like this. Yeah, maybe I rushed through this a little bit, but is this clear why I'm saying it has to be a stiff and this should be a small? Yes? It's not clear? Is it clear or not? So, this relationship is from the things that we talked about last time. So if m is equal to 1, we are good. What we are getting, basically, what we are measuring with the accelerometer is very similar to what is actually acceleration that is being applied to it. Okay? So for that, if you look at this curve, you want to be in this range. Means that you want to have omega, which is a small, so you are in this range. And you have to have certain damping. Okay? Now, that's why you want to have a small omega, and to have a small omega, you need to have a stiff accelerometer. Omega is excitation frequency over the natural frequency. So to get this small, this has to be done. But at the same time, ZR is this, let's say, omega squared times ZG. If we make this too small, then ZR will be very small. You input 200, it multiplied by, I don't know, 0.1, and then you just get 20. I mean, that would be good, but it can be much, much smaller. You don't want that, because that means that your sensitivity is low. So you need to find a compromise. Okay? Any questions about this? Is it clear? I put here 2 videos, so we won't get to look at this in the class, but I expect you that you look at both. The first one is just 2 minutes, and that's just showing you that accelerometer is not the only way to measure displacement or acceleration. And one thing that I also have in my lab is a laser Doppler vibrometer, and how it works is based on Doppler principle. There is a nice video that you can see it. I cannot make it even any nicer than what they did. And there are recent work. This is a TED talk by some guys from MIT, where they use a very fast camera. Just from the video, they extract the modes of different objects. It's 18 minutes. If you're familiar with TED Talks, they're always 18 minutes. So the 2 together is 20 minutes. It's not a big time commitment. This one is totally fun to just watch how they extract everything from the camera. The point of putting this here is that, there are all sorts of other ways to get the displacement. An accelerometer is still being used very widely, but it's one of them. There are other ways to do that. Okay? So we go to Chas seminar now.